Hello class, in this video we will be talking about the law of cosines, which similar to the law of sines allows us to solve properties of a triangle where we have certain information given. The formula is given in your packet and in the slides, which as you can see looks like this. So there are three versions, all of them are exactly identical, and just each one the difference between each formula I'd like to emphasize is that each one has to do with the specific angle of the triangle. So the way that you decide which formula you want to use is dependent on which angle of the triangle you either know or are trying to solve. So notice that the first one says a squared is equal to b squared plus c squared minus 2bc cosine capital A. So in this formula, we have three lowercase letters, which are the sides of the triangles a, b, and c, as well as b and c here. And then lastly, capital A, which is the angle A in that triangle. So there are four unknowns in this formula, and we're going to be using it in situations where either we know all three of the sides, which we call side-side-side triangle, or two sides and one of the angles, in which in either of those cases we could solve the last unknown, and we'll look at how that math works in a couple examples once we get into it. But the way I like to think of it as is like an improved version of the Pythagorean theorem. Like if you look at number 3 here, c squared is equal to a squared plus b squared minus 2ab cosine c. There's a strong similarity to the Pythagorean theorem in that we have a squared plus b squared is equal to c squared. But there's this other component here as well. And one of the ways that I think is helpful for remembering if you had to memorize the law of cosines, is that really it is the Pythagorean theorem adjusted for a non-right triangle. Remember that the Pythagorean theorem only is applicable to right triangles, and this formula is more general. It can actually work on any triangle, and the only difference is the adjustment of this inner product in a way, which when we examine the proof of the law of cosines, we'll kind of see, well, why is this true? But what I also wanted you to notice is, let's say this were a right triangle and C was 90 degrees. If we were to plug that C 90 degrees into this formula, we'd have, well, c squared equal to a squared plus b squared minus this times this times this times the cosine of 90. And from looking at the unit circle, right, at 90 degrees, which is on the top of the unit circle, cosine is 0 because at that point x is 0. So basically, if it were a right triangle, we'd have cosine of 90 is equal to 0, and that would make this entire term 0. So what we'd be left with is c squared is equal to a squared plus b squared. So notice it really is the Pythagorean theorem. It's just better because it adjusts the formula for, well, what if that angle is not right? What will happen? And basically, like, say we were to let's say in the case where we know the angle, we can just plug that in to the cosine of A, and it's a pretty simple formula from there on out, very similar to the Pythagorean theorem, just with an extra term. However, if we're trying to solve the angle, that implies that we know the three sides A, B, and C, little a, b, c, and we'd be wanting to solve for A. And the algebra behind that is in the slides, but I'll walk through that when we do a couple examples. But essentially, we could subtract the b squared and c squared to the other side, divide by this coefficient, because since this is multiplied by this, you can't add this to both sides. You have to first get rid of those terms. So that would leave us with a squared minus b squared minus c squared. And then we could divide it by the negative 2bc, which would leave us with cosine A equal all this stuff. And that's the rule of thumb for solving a general equation like this. If I want to solve for A, I get the cosine by itself first, and then I can apply the arc cosine to both sides to go from there. So, once I've solved for that cosine, I can apply the arc cosine to get the angle A. Or you could just, memorize it in this form, basically a similar formula for solving for particular angles. But before we actually do an example, I wanted to talk about, well, why do these formulas true? Like with the law of sines, it's actually fairly similar in the construction. It's a little bit more complicated than the law of sines, but has a very similar construction. And it all stems from the basic idea that any triangle, whether it be acute, obtuse, or right, can be broken into two pieces which are also right. So like if I took this triangle, which is an acute triangle, to review what that means, acute just means all the angles are less than 90, whereas obtuse means the triangle has one angle which is more than 90. just like, we call it an acute angle versus an obtuse angle. Anyways, we could break this triangle into two right triangles, and then use SOHCAHTOA to help figure some stuff out. Because once we have them in terms of right triangles, we know that the Pythagorean theorem must be true for each of those two smaller triangles, and also SOHCAHTOA must be applied. But obviously, as the law of cosines, we're going to be examining the cosines of angles instead of the sines. Where with the law of sines, we examined the sines of angles B and C and saw how those related back to the height based on the sine ratio. Here we're going to be using cosine. And to start off with the proof, it's helpful to split up the base of this triangle side A into two components, where x is the distance from the height to the left vertex, or the left angle, and L is the length, of the remaining portion from the perpendicular bisector, or not bisector, but perpendicular line to angle C. And then we can examine the cosines and sines. So let's just look at what I have here and kind of we'll see where this goes, because this proof is a little bit hard to reason, where it comes from. But if we start off with the cosine of angle B instead of the sine, notice that the cosine of angle B would be the ratio of x to c, because cosine is adjacent over hypotenuse. And so basically we're looking at, well, what is x and what is L? Those are kind of what we are trying to figure out in this proof. And that's, we'll see why that's important in a minute. But basically, looking at that, we could then figure out, well, what is x? X is equal to c times the cosine of b, because if I multiply across by c, that would give me c times cosine b for this length right here. Then if I wanted to know, well, what is length L? What would that length be in terms of sines and cosines and whatnot? Well, that would be side A minus x, because the whole length is A, and if I subtract away x, that would give me, well, whatever is remaining, length L. So A minus that c cosine B, which we found was x, gives us the length for L. So basically this larger two-term quantity is going to give us length L in terms of the cosine of B. And why do we care about that? Well, we could also then reason about what is the sine of B and use those together using the Pythagorean identities for trigonometry that we discussed a couple weeks ago. But we'll do that in a sec. For now, focusing on, well, what is h? This is in the same way that the law of sines worked. If we, so we use the cosine of b to figure out L, but also we could look at the sine of b to find h. And really, the reason what we're doing here is we know b, we've now figured out what L is, and if we figure out what h is, we know everything about this triangle, and we could use the Pythagorean theorem to figure out the unknowns. And that's kind of where this formula is generated from. But anyways, the height is equal to c sine b, because if I'm looking at side angle B, the sine of angle B would be opposite over hypotenuse, h over c. So if I multiply through by c, I would get that h is equal to c sine b, exactly as we did with the law of sines. So basically, we've solved h, we've solved L, and if we do L squared plus h squared, that should be equal to b squared. And we know everything about this, based on ABCs. So b squared is equal to L squared plus h squared by Pythagorean theorem. And then we can substitute in those quantities which we've solved. We've solved L is this thing from the law of, from the SOHCAHTOA based on cosine, and h is equal to this thing based on SOHCAHTOA sine in each of those two steps. So b squared is equal to this squared plus this squared, and in this term, since it's two terms, we would need to FOIL this all out, and that's what I have here. So basically I'd have a minus c cosine b, and I need to multiply it all through. So that would give us a squared minus the product, or well, plus the product of these two times 2, which is this, plus this squared, c cosine b squared. And this term is easier because it's only one term. That squared would give us c squared sine squared b. Then what's quite interesting about this construction is that what I'm left with is a cosine squared and a sine squared, both which have factors of c upon them. Because we use SOHCAHTOA on this triangle twice, we have that repeated term where we have c squared times sine squared cosine squared. So if we were to factor out the common factor of c squared as I did here, what that would leave us with is cosine squared plus sine squared. And if you recall back from a few weeks ago, this is what we refer to as the Pythagorean identity. Anytime we have a cosine squared plus a sine squared, that is always equal to 1 because of the unit circle. Because remember, cosine is always x on the unit circle. Sine always represents the y position on the unit circle. If we add those together squared, x squared plus y squared, that must be 1 because it's on the unit circle, and by definition, it's a circle of radius 1, which that was its formula. But anyways, what happens is those two terms basically turn into 1, and that leaves me with just c squared. So what I'm left with is b squared is equal to a squared plus c squared minus 2ac times the cosine of b. And there we have it, the law of cosines. And now this is specifically for angle B. We could do the same construction with angle C and with angle A, which would leave us with those other two. Really, they're all the same formula because it's all arbitrary, A, B, and C. It doesn't matter which is which in the triangle when we're using these formulas. Now, it does matter with the Pythagorean theorem, remember, because C must be the hypotenuse. But in this formula, C doesn't even have to be the hypotenuse. It could just be any side. But usually we let A be the smallest and C be the longest, though it does not matter. So that's enough for this video. In the next video, we'll do 2 examples of solving triangles using the law of cosines, and we'll practice implementing this formula and solving the aspects we need to know.